added some more homework problems to the list if you go to my webpage. And I'll do the same this afternoon after the talks. Okay, so let's just quickly review what outer space is. Okay, so we have CVN, and I don't know, you think of it as some kind of a big space, contractible, and a point in it is defined by a triple. So gamma LH. So gamma here is a graph. So finite graph. No vertices of valence less than 3. And then L is a metric or length function. It assigns a positive number to every edge. So this is a metric. Total volume 1. Right, this is the normalization. And then H is a marking from R to gamma, where R is rows. Right? And this is a homotopy equivalence. So you have a homotopy equivalence from R to gamma. Okay, so a point in outer space is represented by a triple like this, and then there is some equivalence relation that maybe I won't review at the moment. And it has a kind of a simplicial structure. It's not quite a simplicial complex, but it's a simplicial complex minus a subcomplex. And this is true in all dimensions. We drew the picture only in rank 2, but the fact that it's a simplicial complex minus a subcomplex is true in all ranks. Okay, maybe I should ask if there are any questions that came up from yesterday about outer space before we launch into today's topic. No questions? Okay, so today's topic is a Lipshitz metric on outer space. Okay, so this is not quite a metric in the usual sense. It's not going to be symmetric, but it is quite useful, as you'll see. Okay, so the idea is that, so we'll need some definitions here. So one thing that I'll simplify is, instead of writing the whole triple, I'll just write gamma, and L and H are going to be understood. So maybe this time I'll put the whole triple, but pretty soon I'll drop the L and H. And so we have two of these, and we'd like to define the distance from one to the other. Okay, so there are some little definitions that we'll need. One is the difference of markings. So okay, so here I'll, for the last time, I will do the whole triple. If gamma, I guess I'm already omitting the equivalence class, the brackets around. And CV n, if you have 2 points in outer space, the difference of markings, a difference of markings, I don't know, what should we call it? I hate to call everything F. What did I call it in the notes? Phi. Phi from gamma to gamma prime is a homotopy equivalence such that the diagram commutes. So there is an obvious diagram here, right? You have the rows, and then you have markings that go to gamma and gamma prime. Okay, and I want this map phi to commute with the markings. It really is a difference between these two markings. So that's another way to think about outer space. I mean, it's a space of deformations of graphs, and you can keep track of there's a preferred homotopy equivalence between any 2 points. Right, you keep track of what you did, in homotopy to go from one graph to another. You could be moving stuff around, folding, who knows what, but in homotopy you keep track of what's going on. That's what outer space is about. Okay, and there's another little definition that maybe I should have mentioned yesterday. You can measure lengths of conjugacy classes because you have this metric. So first of all, a conjugacy class in Fn is the same thing. This is equivalent to having a loop in, or I could even say immersed loop in the rows, right? The rows, the fundamental group of the rows is identified with the free group. And when I say a conjugacy class, then I'm forgetting the base point. There's no base point, and so I don't have a. It's not a base loop. It's just a loop in the rows. Okay. So I can think of a conjugacy class in the free group as just being a loop in R. But then if I have a marked graph, I can push that loop to the graph. Right? So if H from R to gamma is a marking, and alpha is a conjugacy class, which I'm thinking of as a loop in R, then H of alpha is a loop in gamma, right? So I can represent the same conjugacy class in this other graph gamma by pushing it by this marking H, and then I can measure its length because gamma has a metric. So you can make this loop immersed, and then you can just add up the length of edges it crosses with the suitable multiplicity. Okay, so then we define the length of alpha in this graph gamma. So I'm already dropping the triple here. Gamma is really a point in outer space. Okay, so this is the length of edges, total length of edges, the immersed loop. Well, maybe I'll put brackets around H of alpha. So H of alpha by itself may not be immersed, but you can make it immersed, right? You can pull it tight, and that's maybe what the brackets mean. So pull tight. Crosses. I don't know. Maybe just a quick example to make this clearer. So let's say I have in rank two I have my rows, and then I have a graph gamma, and maybe the lengths of the edges are 1/2 and 1/2. But the okay, well let's call this edge x, and let's call this edge y, and let's say this map is it sends A to x and B to xy. Okay, here's a marking, and then I take the conjugacy class, say AB. So I take alpha to be AB, right? That's a conjugacy class in this free group generated by A and B, and I can think of it as this loop, A followed by B. And then I can push it over by H. So H of alpha is going to be, right, A goes to X, and B goes to XY. So I get X, X, Y. So the length of alpha in this graph gamma is going to be 3/2. Right? Because X and Y have length 1/2. If I take A inverse of B, what is the length of A inverse B in gamma? This one is slightly tricky. So what happens when I push A inverse B over? Well, A inverse goes to X inverse, and that's going to cancel out with this X. So I'll just get Y. So this will be 1/2. So this is the meaning of this pulling tight, right? You're not allowed to have a reduced word. You have to reduce it. In fact, cyclically reduce it because it's a loop. It's a conjugacy class. Okay, so those are the main notions we'll need today: the difference of markings and how to measure lengths of conjugacy classes in outer space, at a point in outer space. In fact, this is a very interesting function. See, if I fix a conjugacy class, this gives me a function on outer space, which is continuous. To every point in outer space, I can assign the length of that conjugacy class. And in fact, in the original proof of contractibility, this function was used as kind of a Morse function. It was a Morse theoretic proof of contractibility of outer space, where you study how the topology changes as you increase the levels. It's a very useful function on outer space. Okay. So now we're ready for the definition of the metric. Okay, I'm going to have to erase something, maybe this. Oh, okay, definition. Oh, I should have said, okay. I could have done a little surgery here. Okay, so I said I would omit L and H, but since it's already on the board. Okay, so these are 2 points in outer space, and my goal is to define the distance. So, okay, so I'll just write it down. So the distance between gamma and gamma prime. Okay, so here I'm omitting the triples. It'll be too much. Okay, so this is going to be the infimum over phi of log of the Lipshitz constant for phi, where phi, as phi ranges, as phi from gamma to gamma prime ranges over a difference of marking maps. Difference of markings maps. Okay, so given gamma and gamma prime in outer space, we have a preferred homotopy class of homotopy equivalences between them. But there are many maps in that homotopy class, so I can vary this function over that whole homotopy class. And I want to minimize the Lipshitz constant. So sigma of phi is the Lipshitz constant. Of phi. Okay. So, okay, so what is this? Let me make some comments. First, so I can always assume that my maps are linear on edges. Okay, I can assume, or can restrict consideration to maps that are linear on edges. Well, why is that? Well, because if I have a map, some kind of a map phi that's maybe not linear on edges, then I can replace it by a map that does the same thing on the vertices, but I redefine it on edges to be linear. Instead of going in some a little fast and then slow and so on, I can make it go constant speed, and that can only reduce the Lipschitz constant. It's not going to increase it. So if I'm interested in minimizing the Lipschitz constant, then I may as well consider just maps that are linear on edges. Okay, I will do an example in a minute, but this is just some kind of a quick comment. And then another comment is that the infimum is actually realized. There's always a map that realizes the infimum. So I could put minimum here instead of infimum. This is a consequence of the Arcella-Ascoli theorem. So Arcella-Ascoli, what does Arcella-Ascoli say? Well, in particular, it says that if you look at you have two compact metric spaces and you fix a number k, and you look at the set of k Lipschitz functions from x to y. That set is compact. So in other words, if I give you a sequence of k Lipschitz maps, you can take a subsequence and get a limit. So here you could so you can apply Arcella-Ascoli in our situation here. Gamma and gamma prime are compact metric spaces. And you take a sequence of phis that so that the sigma of phis, that in that of that sequence converges to the infimum, and then Arzelà-Ascoli says there is a subsequence that converges, and that limiting map is then going to have the right Lipshitz constant. It'll realize the infimum. Okay, so Arzelà-Ascoli says that infimum is achieved. Okay, so maybe we'll do an example now. Example. So let's take two graphs that in rank 2 that live in the same simplex, and one is let's see if I'll do the one that I have in my notes. Yeah, one is a rose, and it's here. This is A, and this is going to be B. So A is like this. These are one half and one half, and B is this one. 1/3, 1/3, 1/3. And the difference of markings from A to B, it just sends the, let's consider phi from A to B. Maybe I'll just draw it in the picture. It'll send this base point to the middle of the middle edge, and it'll send this loop here, right? Maybe we'll call it A. It'll send it around here, and it'll send the other loop to the other. Okay, so this loop here will go over here. Okay, that's my difference of markings map. They're in the same simplex, so you could think of A as being obtained from B by squeezing and by collapsing this middle edge. So then this is the difference of markings map. That's the inverse homotopy equivalence. Okay, so let's try to figure out what the slopes are. If I define the map to be linear, yes.
In the definition of difference, then the commutative diagram is commented in the homotopy.
In homotopy.
Then the definition of distance, then the range of pi is in fact the homotopy class of.
Homotopy class, yes. It's a whole homotopy class, exactly. Yeah, the difference of markings is exactly one homotopy class of homotopy equivalences, and you're free to choose any map in that class. Okay, so this map is in the right class. Now, what are the slopes? What is sigma here? Well, so this A here has length 1/2, and it's mapped to a loop of length 2/3, right? So sigma of phi is it's 2/3 divided by 1/2, so that's 4/3. Okay, so we certainly conclude that the distance between A and B is therefore less than or equal than log 4/3. Okay, but maybe how can we be sure that it's not less? Okay, so what would be the argument to show that it's not less? Does anybody have an idea? Right, it's the infimum, so I only know this inequality. Yes.
Did we define Lipshitz? What is Lipshitz constant?
Oh, okay. So no, I didn't define that. But okay, what's the Lipshitz constant? So if you have any, okay, so you have a. In this case, it's just the largest slope on any edge. But in general, if you have a function from x to y, these are metric spaces. Then you say that f is k Lipshitz if the distance between f of x and f of x prime is less than or equal than k times the distance between x and x prime for every x and x prime. And then the Lipshitz constant So the distances get stretched by at most this factor. And the Lipshitz constant, sigma of phi, this is the infimum of k's, so that f is k Lipshitz. And this could be infinity. I mean, in general, there's no reason that a continuous map should be Lipshitz at all. But in our category, all maps can be. I mean, if you make the map linear on every edge, then it's automatically Lipshitz, and the Lipshitz constant is the largest slope on every edge, on over all edges. Okay, so you just have to figure out the slope on these edges. So here it's length 1/2 is going to 2/3, so that means the slope is 4/3. Okay. But how can we be sure that it's not less? So look at the blue curve, right? The blue curve has length 1/2. Now I'm homotopic the map around. Maybe I can come up with some better map, some phi prime from A to B. But it will still have to send this blue curve to a curve that's homotopic to the curve I drew, right? Because it's whatever my map is, it will have to be homotopic to this map. So what can the length of the image of A be? It's not going to be less than 2/3, right? This is the smallest it can possibly be because this is immersed, and so you can never do better than 4/3. So more formally, what you say is that well, okay, let's write a lemma like this. So if phi from A to B is I don't know, let's say k Lipshitz, then for every conjugacy class alpha, the length of alpha in B is less than or equal than k times the length of alpha in A. Okay, that's what we just observed here. Right? I take my conjugacy class represented by a curve in A, and it has a certain length. Now, when I apply my map, which is k Lipshitz, that loop, the image loop is going to have length at most this. K times the length. K times the length it had before. Just because a k Lipshitz map can stretch things by at most k. And then maybe you have to do some cancellations. Maybe you have to do some tightening. So then in B it might be less than that. But you still only have this inequality. Right? In other words, maybe another way to say this is that maybe I'll state this as a corollary. The distance between A and B. You see, this is the log of k for a smallest possible k. This is greater than or equal than log of length of alpha in B divided by length of alpha in A for every conjugacy class alpha. Right? I take the log. I divide by the length here, and then I take the log. Log k is going to be the distance if I choose if I choose phi to be the minimizer. So I get this inequality here. So this is how you can estimate distances from below. Right? This gives us, finding a particular map gives us an estimate from above. Just look at the maximal slope. But to get estimates from below, I can look at these curves. And in this example, we in fact found a curve so that the upper bound and lower bound agree. So now we know that in fact the distance is exactly equal. So the distance between A and B is exactly equal to log 4/3. Okay? Is that clear? Okay, let's do it the other way now. Let's go from B to A. And then we'll do make some more general statements. Okay, so another example. I want to compute the distance from B to A. And it's not going to be log 4/3. So you'll see it's not symmetric right away. Oh, by the way, so this is not the only minimizing map. Can you see another minimizing map here? So these minimizing maps may not be unique. Yeah, so this middle point, at this point, the vertex doesn't have to go to the middle. It can go anywhere on this edge, right? So there's a whole interval's worth of minimizing maps. Okay, so what is the map from B to A? Well, first of all, what is the right difference of markings map? Well, it's you collapse the middle edge, right? That's the. Okay, so I collapse this and I send A to A and B to B, like that. That's the map. Okay, so what are the slopes? So let's call it I don't know, phi C. What is sigma of C? So the slope on the middle edge is 0, but on these two edges, so an A has length 1/3 and it goes to something of length 1/2, right? So the slope here is 1/2 divided by 1/3, which is 3/2. Okay, so I want to say that the distance between B and A is equal to log 3/2. I mean, this part only shows less than or equal, doesn't show equal. But what is is there a curve that witnesses the lower bound? What's the curve? There is a curve. The one, that's right, exactly. So the one that goes around both ends, this curve here, which is something like AB inverse. So that's a curve of length 2/3, and it goes to a curve of length 1. Right? Alpha, yeah, AB inverse, the length of AB inverse in B is 2/3, and the length of AB inverse in A is 1. So that's a witness that the distance is log 3/2. Okay? Okay, so here's a basic proposition, and then we'll do the kind of the main lemma in this subject. Okay, let me erase this. Although I want to make some other comments before we launch into that. Okay, but no, basically the simple proposition is like this. Okay, so first you have the triangle inequality. And you have to be careful how it's not symmetric, so the order is important here. The distance is always greater than or equal to 0, and equality is equivalent to gamma being equal to gamma prime. So for distinct points, it's strictly positive. And it's invariant under the action. So phi is an element of out Fn, and the action is on the right. I act on gamma and gamma prime by the same automorphism, and I don't change the distance. for every phi in out fn. Okay, so it's an out fn invariant metric, non-symmetric metric. Okay, so number 2 is the most interesting statement here. The one, okay, so what should I say? Let me say some words here. One is just a consequence of the fact that when you compose maps, the Lipshitz constants multiply, right? So the sigma of, I don't know, fg is less than or equal than sigma of g times sigma of f. And so when you take logs, this becomes additive. Right? Number 3 is also easy because the difference of markings is the same. So the difference of markings for gamma gamma prime and gamma phi and gamma prime phi are the same. Right? We have this kind of a picture here. There's the difference of markings for gamma and gamma prime, but then you compose with this phi to go to these two graphs. Well, you can compose, but it's still the same phi. That's the difference of markings. Right? Does that make sense? Okay, what about number 2? Okay, well, what would it mean to say that the distance is negative? Okay, how can the distance be negative? Okay, suppose the distance from gamma to gamma prime is negative. Okay, well that would mean, so then there exists a difference of markings phi from gamma to gamma prime with the Lipshitz constant strictly less than 1, right? That's what it means. So I can look at the images of edges in gamma. So I take an edge in gamma, it has a certain length, I look at its image. In the image, it'll have strictly smaller length, right? Because the Lipshitz constant is less than 1. And so that means that the the images of edges from gamma cannot cover all of gamma prime, because they both have volume 1, the same volume. But the images of edges are too short to cover 1. Okay, so then phi is not surjective for volume reasons. Right? I mean, the volume of phi of gamma is less than 1. But that's a contradiction. We have these graphs without valence 1 vertices. There is no homotopy equivalence that's not surjective. Every homotopy equivalence is surjective. Contradiction. As phi is a homotopy equivalence. Okay, what about the equality? If in other words, if the distance is 0, suppose the distance from gamma to gamma prime is equal to 0. So then what happens? So then we have so this is just a variant of this proof, right? So you just have to think a little bit harder. So then we have phi from gamma to gamma prime, and it has so sigma of phi is 1. And it has to, so the slope actually has to be equal to 1 on every edge, otherwise you'd get the same contradiction. You wouldn't have enough volume. So phi must have slope 1 on every edge. And it also has to be, it has to be onto. And furthermore, if I take two different edges, their images can only overlap in points. Right? Otherwise, you would lose too much volume. The images of edges can overlap only in points. Now, the overlap has to have volume 0. Otherwise, the map wouldn't be surjective. Okay, so what does that mean? Well, that means that phi is kind of a quotient map. Gamma prime is obtained from gamma by taking pairs of points and identifying them. Right? Because phi is surjective, and the map is basically injective except for some collection of points. So you can start with gamma and you identify certain pairs of points and you get gamma prime. That's what the picture here. But the ranks of gamma and gamma prime are the same, so you cannot actually identify any points. Okay, so this is simple. So then, so it follows that that phi identifies collections of finite collections of points. But that's impossible since gamma and gamma prime have the same rank. Right? If you identify a pair of points, the rank will increase. So in fact, phi is an isometry. So phi is an isometry. There are no identifications of points. And so that means that gamma is equal to gamma prime. We have an isometry. If you have an isometry in your homotopy class, so difference of markings class, then the 2 points are equal by definition. Right? That was the definition of the equivalence.
To show this situation in picture.
Yeah. Okay. So. So let's say gamma is something like this, and for all I know, so I don't know what gamma prime looks like, maybe, but I do have this map phi, which is it has slope 1 on each edge. So it maps every edge isometrically into gamma prime, and moreover, the images of the edges are basically disjoint, except for maybe some. It could be that one edge goes like this and another edge goes like this. They could intersect in points. The volume of the intersection must be 0. Otherwise you would, the volume of the image would be less than 1. So in other words, what happens is that this gamma prime is obtained from gamma by identifying, like if I have this edge that goes this way and another edge that goes the other way, then some point over here is identified with some point over here. And there may be other pairs like this, but finitely many. Okay, so then I'll know that gamma prime is obtained from gamma by identifying these points. But that can't be because then gamma prime would have a larger rank than gamma. So it must be that in fact there are no intersections like this at all. In fact, phi is then an isometry. So there are no identifications at all. It's a slope 1 on every edge, and it's 1 to 1 and onto. So it's an isometry. Does that make sense? Okay. Right. Okay, maybe a couple more examples before we. The proof of this main lemma is going to take us a while. So I think I should probably wait until after the break to start that. But maybe I'll give you some more examples here. let's see. What happens if I take, I'm still in rank 2, and I take one point to be our favorite rows, and the other point maybe will go to infinity in outer space. So here's a point B, and it's very close to the missing vertex. So A is like this, 1/2, 1/2, and B is I guess 1 minus epsilon, epsilon. Okay. With epsilon going to 0. What are the distances now? Let's compute that. From the distance from A to B, what should that be? Can you just look at the picture and tell me?
1 over 3,
What?
1 over 3, 7.
1 over... No, let's see, no. Wait, 1 over, maybe I didn't say, what? Say again?
Log 1 over 3.
1 over 2 epsilon. No. I think you're thinking the distance from B to A. Is that what you're doing? Maybe you're doing the distance from B to A. Log of 1 over 2 epsilon. You're right about this, yes. But that's the distance from B to A. What about from A to B? What? Log of 2 times 1 minus epsilon, right? This is the curve that starts out as 1/2 and then goes to 1 minus epsilon. And that's the, right? Does everybody see this? Now, what kinds of numbers are these? This is certainly less than log 2, right? Well, this thing goes to infinity. So so the way to remember this is that you're operating a spaceship, and you charge passengers to go to the edge of outer space. You only charge them log 2 once. But to bring them back, you charge them this amount. It's cheap to go out into outer space, but it's expensive to come back. Okay. Okay, so the following definition is somewhat useful. It's a notion of a witness. So to compute distances, right, you always have to find these curves that stretch the maximum amount. So we'll call them witnesses. Okay, so definition. So let's say gamma and gamma prime are in CBN. Then a witness is a conjugacy class alpha such that the distance between gamma and gamma prime is equal to log length of alpha in gamma prime divided by the length of alpha in gamma. Right? We always have greater than equal by what I said a minute ago. That this always gives you lower bounds, but the witness is the one that actually realizes it. And the main lemma in the subject, which I guess we'll start talking about it. We're still 15 minutes. The main lemma in the subject is that witnesses always exist. And the proof is going to introduce the concept of train tracks. Okay, so it's an interesting proof. Other questions? I'm not quite sure if I should start doing the proof because we'll take a break in the middle. So if you have any good questions, yes. Yes.
Is there a meaningful metric to symmetrize the symmetry metric?
You can symmetrize and you'll get a symmetric metric. But it turns out this in this form it's more useful than if you symmetrize. The reason is going to be so for those who know about Teichmüller theory, there are these mapping classes called pseudo-Nassovs, and in Teichmüller space they have an axis. They're loxodromic, and the translation distance along the axis is log of the dilatation. Is the log of the dilatation of the pseudo-Nassov. In other words, the Teichmüller distance has a meaning in mapping class group theory. You can see it from the pseudo-Nassov. The same thing will happen in outer space. There are these automorphisms called irreducible. They play the role of pseudo-Nassov homeomorphisms. They also have they act hyperbolically in outer space. They have axes in outer space. And if you look at the translation distance with respect to this metric, this asymmetric metric, it will be log of the dilatation. And somehow non-symmetry is imposed on us because it turns out that typically an automorphism and its inverse can have different dilatations, unlike in surface theory. In surface theory, a pseudo-Nassov and its inverse have the same dilatation. But in OutFN, that's not the case. And so if you want to keep this feature of having the correct translation distance, then you have to live with the non-symmetric metric. You could symmetrize it, and that'll give you a metric that is compatible with the topology of outer space. You could define a topology on outer space by saying it's the metric topology with respect to the symmetrized distance. But it will be less useful for the purposes of understanding what automorphisms do. Okay. All right. Well, we can start talking about this, and the actual proof will happen after the break. But I'll introduce some notions here. Yes.
So here, if you're going out to the boundary of the outer space, the distance is finite.
That's right. So So this is like a Weil-Petersen metric. See, that's for those who know about Teichmüller theory. So it's like in other words, it's not complete. I can the sequence of these B's forms the Cauchy sequence, and but it doesn't converge. So you can form a completion by adding these points. However, it turns out that these are sort of forward Cauchy sequences where you're measuring the distance from a point to the point to points afterwards. But you could also do it the other way. You could measure points, when you're defining Cauchy sequences, you could do it back in reverse. You have a sequence, but you measure the distances from the more advanced point to the point backwards. So that one turns out to be complete. So it's an interesting mix of kind of Teichmüller distance and the Weil-Petersen distance. Okay.
I didn't finish my question. So is there a meaningful way of looking from the boundary?
Is there a meaningful way of what?
Meaningful way of defining a boundary of outer space.
I wasn't going to talk about the boundary, but So the boundary can be defined without the distance. You can take just like in Teichmüller space, you can talk about length functions, and you can map the. We'll touch on that too, but you can map outer space to the space of length functions. For every point in outer space, you have lengths of all conjugacy classes. So you can just map it to some abstract space of functions, and then it'll turn out that the closure inside there is compact, and that's the standard compactification of outer space. You can think about the completion with respect to this metric, and that's also been worked out. It's not exactly the same. You don't get the same space. You don't get something compact. You get something complete, but not compact.
But both of them are both of the compactifications of the mixed outer connection.
Yes, yes. Yeah, everything is equivariant here. Okay. Okay, well, maybe we'll start with a certain definition. Okay, so this is towards the proof, but definition. So if so, first of all, phi from gamma to gamma prime is an optimal map if sigma of phi is equal to, well, if log sigma of phi is equal to the distance from gamma to gamma prime. In other words, if phi realizes the Lipshitz constant, then you call it an optimal map. You cannot do better. This is the best Lipshitz map you can have. And these are not unique, right, as we saw. Okay, another definition, the tension graph. The tension graph, delta phi, of an optimal map phi is the union of all edges where the slope is equal to sigma of phi. So this function phi has a slope equal to sigma phi on some of the edges, but perhaps smaller slope on some other edges. You just take the ones where the slope is maximal. So in our examples, we had two examples. This one goes here, and this one went here. These tension graphs were, in the first case, the tension graph was everything. Right? The slope is the same on both of these. But in the second example, the tension graph was just a circle. The edge in the middle collapsed. So the slope there was 0. Right? Okay, so these are tension graphs here in our examples. All right. So now, if I have a point, say a vertex in the tension graph, then I can consider directions out of it. Okay, so if V is a vertex of the tension graph, delta phi, denote by TV of delta phi, the set of directions at V. So this is so what do I mean by this? Well, so if I have a vertex, here's a vertex V of the tension graph. There are 4 directions. There are 4 directions out of it, right? There are 4 different ways of leaving V. So in this case, this set would consist of 4 elements. So this is like, the analogy is like the unit tangent space. If you're in a manifold, you can look at the set of directions out of a point, and those are unit tangent vectors. Well, here in the graph, this kind of unit tangent space is a finite set. There are only finitely many ways of leaving a point. And here it would be just 2, right? In this case, there are only 2 ways of leaving this point. I don't consider directions that leave the tension graph. These are just directions within the tension graph. Okay, now the map phi induces a function on these unit tangent vectors. It's kind of a derivative. right? So if there's phi star, so phi star acts, or phi acts as a, well, phi acts as a derivative which will denote phi star. And it goes from TV of delta phi into T phi of v, right? You look at the image point and you're looking at the directions in gamma prime. Right, so for example, in here you have so this vertex v goes to the middle over here. This is phi of v, and then two of these, the northwest and northeast arrows, they go north, right, and then the other two go south. That's the function. It sends these two vectors to the vector pointing up, and the other two vectors to the vector pointing down. And over here, I guess, well, I don't know exactly how, but anyway, it's something like this, right? These two vectors will go to two vectors like that. Okay, so that's the derivative of phi. Okay, so the next concept is that of a train track structure on delta phi, and this is somehow the most important concept today. So maybe it's a good time to take a break and then continue.